Welcome to our video on factoring trinomials. We have six objectives on this one. It seems like a lot, but they're really all just different ways of factoring slightly different trinomials. And a trinomial is just a fancy way of saying a polynomial with three pieces. And then we're going to see later on a more specific version of a trinomial is the quadratic, which is a very important function that comes up a lot in many multitudes, econ, physics, all over the place, right? So it's really good to get familiar with how to work with trinomials. Now, the first easiest kind of trinomial to factor is one where the leading coefficient is 1. Well, what the heck is a leading coefficient? The leading coefficient is the number in front of the highest power in any polynomial, right? So when we list polynomials out, we're always supposed to list them in descending order with the highest power first down to the lowest power. And then if there's a constant term, of course, that goes last because that has a power of 0, right? Anything raised to the power of 0 is just 1. So 12 is really 12 times x to the 0, right? So this would be a typical trinomial. It's actually a typical quadratic, which I know seems misleading because quad means 4. So why does a quadratic only have 3 terms? Oh, don't get me started. But that's what it's called. You'll see quadratics a lot. Anytime you have a piece that has a squared coefficient, or sorry, a squared variable, and then a linear term, right? A term with just the variable raised to a power of 1, and then a constant. If you've got those three pieces, that's a typical quadratic. Now, when we factor these things, if the leading coefficient, the thing in front of the x squared, or the squared term, right, is a 1, we know it has to factor with x plus a times x plus b, or it could be minus minus or plus minus, right? So these signs, pluses, could be both minuses or one or the other, depending on the signs here. Because these are both pluses, these both have to be pluses. If this one is a minus and this one is a plus, then they both have to be minuses. If this one is a minus and this one is a minus, then they have to be opposite. One has to be positive, one has to be negative. So that's just something you kind of learn from experience. But also, if you think about how this works, we know it has to factor into this form where a times b, right? So these are numbers, by the way. A and b are just going to, we just don't know what they are, but they're going to be, like a 2 and a 7 or a 3 and a 5, that kind of thing. So a times b always has to equal the constant term. So it has to equal 12. So if this is a plus 12, you would have to have like plus 2 times plus 6, or negative 3 times negative 4, right? Because two negatives end up being a positive when you multiply them together. But if these are both negative, then when you do the inner and outer pieces, when you're kind of like foiling, you would get this piece would be negative, right? So that's why if this is negative and this is positive, we know they're both negative. If this one is negative and this one is negative, the only way to get a negative term here is if these are opposite signs, or so one's positive and one's negative. If this one's positive and this one's negative, it's the same thing. It's still one or the other, right? So it all kind of comes down to this thing. If this is positive, they're either both positive or both negative. If this is negative, they're one or the other. And then determining if they're both positive or both negative comes from looking at this, right? So if that's positive, they're both positive. If that's negative, they're both negative, but only when the second one is positive. So it's kind of like a two-step process. Look at the second one. The thing in front of the constant, that's first. That tells you if it's positive, you're going to have the same sign. You're either going to have both positives or both negatives. And then the second stage is you look at this first one, and whatever that is, that's what those two signs are. If this, then other scenario, look at this one first, and if it's a negative, you know they're going to be opposite signs, and you're just done. Okay, so the rules are a times b is the constant term, and then a plus b, right? These things have to add together to be the number in front of here. Now that's only when this is a 1. When this is something other than a 1, this rule changes slightly. So in order to figure out how it works, it's kind of a trial and error. We know that it has to be, x plus a, x plus b kind of thing, and a and b have to multiply to 12. So let's list out all the possible factor pairs of 12, i.e. two numbers that multiply together to 12. So 1 and 12, 2 and 6, 3 and 4, and then of course the two negative combinations, -1, -12, -2, -6, and so on and so forth. But because that 7 is positive, we know we have to be using the positive numbers because you can't add two negatives and get positive 7. So now you're asking yourself, are any of those two pairs such that when you add them together, you get 7? Well, 1 plus 12 is 13, 2 plus 6 is 8, but 3 plus 4 is 7. Ta-da! There's our winner, and we know it factors to x plus 4, x plus 3. Okay, so it's kind of a factor by trial and error, but there is some logic in knowing what's going to work and what's not going to work. And then, of course, you can verify it by multiplying those two things out, foiling, and seeing that you do actually get back to the original thing. So to sum it up, if you're factoring a trinomial and the leading coefficient is a 1, you follow these steps. First, you write the trinomial in descending order. As I talked about, you should always have your polynomials in descending order of power. So highest power first, then next power, and then down to the constant. List the factorizations of the third term of the trinomial, i.e. take the constant term and list all the factor pairs. Something times something equals that number, something times something equals that number, list them all out. Pick the factorization where the sum of those two numbers is the same as the coefficient of the middle term. And then Bob's your uncle, you're done. So here's another example, right? It's already in descending order, so we don't have to do anything with that. We're going to look at all of the factor pairs of 8, so it's 1 and 8 and 2 and 4. But since this one's a negative, right, the second number's a negative, we have to look at the negative versions. -1, -8, -2, -4. And which of those two pairs would add up to -6? This would give me -9, this would give me -6, so we know it has to be that pair. So it's going to be those two of -2 and -4. Put those into the formula. X plus a, x plus b becomes x plus a -2, right? X plus a -4, which is just x minus 2, x minus 4. And that would be the factorization for our original polynomial. If we did all the foiling, we would get back to the original and go, yep, it works. And that's always a good idea to check your work. Okay, how about we kick it up a notch and now look at one where they're going to factor where the leading coefficient is something other than a 1. It's really the same idea. We just have more combinations to consider. That's really all that happens. So now we have that leading coefficient of 5x squared. So instead of x plus a and x plus b, we know we have to have this generic looking thing where we have ax plus b and cx plus d. It's a big fancy way of saying I have to have two x terms and I have to have two constant terms. The two x terms still have to multiply together to give me the leading term. Before it was x times x because that gave me x squared. Now I need something times something to give me 5x squared, and the only way I can do that is 5x and x because there aren't any other two numbers that multiply to 5. Now, if this was a 4, we would just have more things to check because it could either be a 4x and an x, or it could be a 2x and a 2x, right? So it's just going to add more things to check. But the rules are still the same. The first two terms have to multiply to the first term, and the second two terms, right, the two constants, have to multiply to the last one. So b times d has to be 2, and there's only one way that can be, 1 times 2. Of course, it could be -1 times -2, but that's not going to work with a positive, right? So since these are both positive, we know everything has to be positive. So we kind of know what we have to try. It has to be a 5x and an x. It has to be a 1 and a 2, but it could be the 1 could go in for b or the 1 could go in for d. So that's really the only thing to check at this point. And then we know that when we do this inner piece and then this outer piece, those two things add together to give me 7. So this is where trial and error comes in. Let's look at the next slide. We really only have two options. It's going to be 5x plus 1 times x plus 2, or it's going to be 5x plus 2 times x plus 1. And we could also have negatives, but the negatives won't work because when you do inner and outer, right? So like for instance, this would give us -1x. This would give me -10x. And when I add those two together, that gives me -11x. There's no way I'm going to get a positive 7 with negatives in the middle, right? So we know right off the bat, the negatives are no good. So we're just going to try these two. And when we do this inner, this gives me 1, and this gives me 10. And when you add those together, that's 11. That doesn't work, okay? This gives me 2, this gives me 5, that gives me 7, right? That's 2x and 5x, that's 7x. So I know it has to be that one. So that's what we mean by trial and error, that you're really just kind of guessing and checking, but you're not guessing blindly. You're using some logic to figure out, kind of eliminate options. I know the negatives won't work, so I can ignore those. And now let's try these two and see which one works and which one doesn't. Okay, determine whether a trinomial is factorable over the integers. So far, all of these examples we've seen, we factored them so that all of the little bits and pieces, all the numbers inside those parentheses were all whole numbers, i.e. integers, right? Well, not all trinomials, quadratics, they don't all factor to nice, pretty integer coefficients. It's just not the case. Now, most of the ones you're going to see are probably going to factor with whole numbers, but it doesn't always work out that way. And there's a really easy way to figure out if it's going to factor that way. And it's by looking at this little discriminant piece, this b squared minus 4ac. It's called the discriminant. Doesn't matter. You'll see that later. Who cares what it's called? But the bottom line is if you hear somebody talking about a discriminant, this is what they're talking about. So all you have to do is plug in the numbers for b, a, and c based on this formula, right? It's in the form ax squared plus bx plus c. That's something you're going to kind of have to memorize because you're going to see that a whole lot. But in any case, you plug in all those bits and pieces and do this simple math of b squared minus 4ac. If that number is a perfect square, then the trinomial will factor with integers. If it is not a perfect square, but it is bigger than 0, right? So it's a positive number, but it's not a perfect square. The thing will factor, but it'll have what are called irrational roots because the numbers will involve square roots, right? If you do this and the number comes out to be 0, then you're going to get only one solution. And if that number comes out to be negative, you get no solutions. They just don't exist in the real numbers. You would get imaginary number solutions, which you only deal with imaginary numbers in very special math classes. Okay, for us, all we care about is whether or not it's a perfect square. So something like this, we know that A is 5, B is 7, C is 2. Plug it into the formula, right? A, B, and C. So 7 squared minus 4 times 5 times 2. 49 minus 40 becomes 9. 9's a perfect square, and we know this will factor with perfect whole numbers. Well, we already saw this example. We know that it factors to 5x plus 2 times x plus 1. But before we did all that work, we could have checked really quick that it would have worked because you don't want to waste a lot of time trying to factor something that won't factor. So it's always nice to check these things really quick and see if it works. Now, like I said before, if it equals 0, then the two factors end up equaling each other. What it means is you only have one solution because you would have something like, let's just say, right, you would have 3x plus 2 times 3x plus 2. That means you only have one solution to this thing because you have two factors that are the same, and when the two factors are the same, you only have one solution to this thing. Okay, determine whether this one's factorable. So what is A? A is 3, B negative 4, and C is negative 4, right? So don't forget that the original formula was ax squared plus bx plus c. So those become negatives. When you plug those in, negative 4 squared is 16. Negative 4 times 3 times negative 4, that becomes positive, right? So it's basically positive 4 times 4 times 3, which is 48. 16 plus 48 is 64. 64 is a perfect square. It's 8 squared. So that one is going to have nice, pretty, perfect integer factors. And then we could go ahead and do the work, right? We know the only way that three factors is a 3 and a 1, so we know we have to have a 3p and a p. Now you might be asking yourself, how do I know it's 3p and p and not p and 3p? Does not matter. Doesn't matter which one gets the 3 and which one gets the 1, because we're going to switch these numbers around anyway. So what I mean is we could have 3p plus 4, right, times p plus 1, if we thought 4 and 1 were the numbers, or we could check 3p plus 1 and p plus 4. And you go, well, if you switch places with the 3p and the p, so let's say we're going to switch this one. Well, that just becomes p plus 4 and 3p plus 1, right? But isn't p plus 4, 3p plus 1 the exact same thing as this? They're just in opposite orders? Yeah, so that's why it doesn't matter. Okay, so now that we know it has to go 3p and p, the question is, what about the last two? Well, we know they have to multiply to be -4. So we're looking at 1 and 4 or 2 and 2, where one of them is positive and one of them is negative. So you're just going to look at all the different combinations here and see which ones give us a -4p on the inside. Remember, the inside is when you do the two inners and then the two outers. So if you check this one, this would give me 1p and -12p. Ooh, well, that's going to be too big, right? It's going to be -12 plus 1. It's going to be -11. Okay, how about a -1 and a +12? Also, those two numbers are too big, right? Or too different, right? You've got a 1 and a 12. You want things that are closer together because you only want a difference of 4. So how about this? A -4 and then a +3. Well, that gives me a -1. Or a 4 and a -3. None of those seem to work. Okay, so let's switch over and try 2 and 2, because don't forget that 4 factors as 2 and 2 also. So then you try this or this, right? Because the only combination is now which one gets the positive, which one gets the negative. So this is a 2 and this is a 6, and we can see the difference between 2 and 6 is 4, but we want negative, right? So +2, -6 gives me -4. This would give me -2 and +6, which would be +4. That's why the one in red is the winner, and that's how it factors. Okay, so how do we factor trinomials? Well, write it in descending power order like we always do. Factor out any greatest common factor. Remember, we've talked about this in other videos that you always try and factor out a greatest common factor if possible. And then once that's done, it's just a matter of trial and error. We know it's going to be of the form ax plus b times cx plus d. Sometimes a and c are both 1. So instead of thinking of two different ways, whether the leading coefficient is 1 or not, right? If it's 1 or something else, it's always going to factor to this form where b times d is the constant term. ax times cx is always the leading term, and if the leading term has a coefficient of 1, we just know a and c are both 1, right? So we can generalize that. Then here's those rules about when we have pluses and minuses and that kind of stuff. Then it's just a matter of listing out all of the binomial factors, i.e. all of the pairs of numbers that multiply to that constant term. And then it's a matter of just guessing and checking, right? Writing them all out, making sure you try every combination and see which one works when you FOIL it out. Okay, how about factoring a trinomial using substitution? Well, the only time we really do this is when we recognize something as a trinomial in this weird form. So hopefully you can kind of see that I have something here that's being squared, and then I have that same something that's being multiplied by a constant term, and then I have just a constant term. Well, that's a quadratic in disguise, because it's got something squared plus a linear term plus a constant, only now instead of it being like x squared plus 7x plus 12, it's all this junk. It's x plus y quantity squared, and then 7 times x plus y. So when they talk about solving this by substitution, all we do, all right, so as I was saying, we recognize this as a quadratic in form, and we do a substitution because this just looks confusing and ugly and weird to our eyes. But if we let z equal this x plus y thing, then by substitution we just get z squared plus 7z plus 12. And that's a lot easier for us to see and understand and visualize, and then we can use our simple trinomial, rules. We have a leading coefficient of 1. We know the two constants have to multiply to 12 and add to 7, so that's obviously 4 and 3. So we know it has to be z plus 4 and z plus 3. Now, if you're thinking, how the heck did you get 4 and 3? Just go through the steps, right? List all the factors of 12, then write out all the possibilities, so it'll be like x plus 2, z plus 2, z plus 6, z plus 1, z plus 12, z plus 4, z plus 3, and then FOIL all of them and see which ones work. right? 4 and 3 is going to be the only one that gives you 7. And then, because we weren't dealing with z's, we were really dealing with x plus y, so you put them back in. So instead of z plus 4, it's x plus y plus 4. And then instead of z plus 3, it's x plus y plus 3. And there are your two factors. Okay, so it's just a way of kind of factoring more ugly things using the same simple rules, because we do substitution to make it look a lot simpler. All right, then we've got this factor or trinomial by grouping. You can see that we're spending a lot of time figuring out how to factor these trinomials, because factoring quadratics is extremely important. Like I said, they come up a lot in a lot of different aspects. So you really want to practice this a lot. Okay, how about factor by grouping? We're looking for trinomials that are still of that basic ax squared plus bx plus c. So a simple example would be, your 6x squared plus 7x minus 3. So a is 6, b is 7, c is negative 3. And we go down to find the product of a times c as being negative 18. This is called the key number. We can list out all the factors of negative 18. So 1 and 18, 2 and 9, 3 and 6, and of course we just have to change which one is negative and which one is positive. Those are all the factors, or factor pairs, I should say, of 18. All right, once we have that, we find the two factors of the key number whose sum is 7. Why 7? Well, if you remember, because 7 was that middle term, right? So negative 2 and 9, those sum to 7, right? Because 9 plus negative 2 is 7. So we used those two coefficients as the two terms where the sum is positive 7. So instead of 7x, we turned it into 9x plus negative 2x, right? So all we're doing is taking this middle term of 7x and turning it into 9x minus 2x. Everything else stays the same. All right, step 5. Now that we've done that, here's my 9x plus 2x, right? Now that we've done that, we're going to factor by grouping. Factor by grouping basically just says take 2 of your 4 pieces, right? You notice you have 4 pieces, the 6x squared, the 9x, the negative 2x, the negative 3. There's 4 pieces. So take any 2 pieces that have something in common and factor that common piece out. Now you'll notice I said any 2 pieces because you really could pick any 2. All right, let's just, for giggles, pick the first 2. So if you want to factor those 2, what do they have in common? They both have an x, right? And then 6 and 9 both have a 3. So I can factor a 3x out of them, and then what's left? This would be 2x, and then wouldn't this be plus 3, right? And then you look at the second 2 and go, what do they have in common? They don't have anything in common, other than maybe a negative 1. And of course, you pull out a negative 1, and you're left with the 2x plus 3. The bottom line is when you move to the second set, you want to have whatever was in your parentheses from the first set also in the second set. So you're kind of like asking, okay, how can I get a 2x plus 3 out of this? Let's say you did it differently. Let's say you picked these 2. What does 6x squared and 2x have in common? Well, you can take a 2x out of them, right? And this leaves you with a 3x and a minus 1, right? Then you get these 2 pieces, and what do those have in common? Well, they both have a 3. And what's left? 3x minus 1. Oh, hey, look, I've got 2x plus 3 times 3x minus 1. The same thing, right? So it doesn't matter which 2 you choose. Pick any 2 that have something in common and go from there. Now we can try it with this one. A is 10, c is negative 3, a times c is negative 30. List out all the factors of negative 30. So 1 and 30, 2 and 15, 3 and 10, 5 and 6, and then we're just same thing, but changing the which one is negative, which one is positive. Okay, now we're looking for one of those pairs whose sum is negative 13. Well, 30 and 1, whether it's 1 and negative 30 or over here, 30 and negative 1, when you add them together, isn't it going to be a version of 29, right? So 1 and negative 30 is negative 29. 30 and negative 1 is positive 29. So the reason why I'm pointing this out is you don't need to waste your time checking all of them. Just check one of the sets, and we know the other set is not going to work, right? So 2 and 15, the difference between those is, hey, 13, right? So 2 and negative 15 gives me negative 13. Over here, negative 2 and positive 15 gives me positive 13. But we wanted the negative 13, so it's going to be these two, negative 15 and 3. It's that simple. There's our two pairs. We split it up, 2x and negative 15, and then go from there. Factor by grouping. Now in this case, you can factor however you want. Pick the first two, take the 2x out, and you're left with this. And then the second two, you can take a negative 3 out, you're left with the same thing, and there's my factoring. But like I said, you could have also gone like 10x squared and negative 15x and done it that way. It just doesn't matter. Any two that have something in common, factor it that way. All right, I know this is a long one. Sorry, guys. Our last thing, factor a polynomial with 4 terms by grouping a trinomial. Sounds like a lot, but it's really what we've kind of already been doing. So factor this thing. Well, you could only factor this thing if there's something you can do with these 3 pieces, because you see how those are a different letter, right? X and X, and then this is Z. So you could really only try and factor this by grouping, by taking these two and take out what they have in common, and then these two and take out what they have in common, because you couldn't pair up the Z with anything else, and it wouldn't have anything in common, right? Because there would be X's in all the other pieces. And when you put these two together, they have nothing in common but 1. So that's not going to help. So factor by grouping. Anytime you see 4 pieces, your first thought is factor by grouping. And that doesn't work. But then if you look again, you go, hey, these 3 pieces give me a typical trinomial, a typical quadratic. And then this piece is a squared, right? So I kind of have difference of squares with these two things, but I have this extra junk. So maybe if I just take these 3 and treat it like a quadratic and kind of ignore the z piece, let's see what happens. Well, so if we factor x squared plus 6x plus 9 as a leading coefficient of 1, so we know it's going to be x plus something times x plus something. 9 factors to 9 and 1, that's not going to give us 6, but 3 and 3 gives us 6, and oh, hey, look at this. It ends up factoring as a perfect square. It's now x plus 3 squared minus z squared, and you go, hey, difference of squares, we just learned that in another video, and I know how to factor difference of squares. It's the first term minus the second term times the first term plus the second term, right? So here's x plus 3 plus z, there's that plus that, and then x plus 3 minus z. And we've just factored this really super weird thing. All right, guys, sorry for the long video, but those are all kind of the different ways that we can factor trinomials, or what we also call quadratics.